Today we want to continue talking about complex roots. And that's why we had to have all those complex numbers and talk about polar coordinates. It's really going to come to land in complex roots. This is just going to be like talking about square roots, but more of it. So let's see how this is organized. First, we're going to observe that numbers have two complex square roots. There are two square roots. They'll be 180 degrees apart in the complex plane. Note that when we use the radical symbol, we're referring to the principal square root. So the radical symbol, that refers to the principal or the positive square root. So when we write the radical symbol, if I want to refer to the negative square root of 4, I have to put a negative in front of the radical. But if I just write the square root of 4, the answer is 2. We just write 2. But 4 has two square roots. Positive 2 and negative 2. If we use the radical symbol, we were talking about the positive one. But if I just say, what are the square roots of 4? 2 and negative 2. If we write them as complex numbers, that would be 2 plus 0i and 2 minus 0i. Or sorry, minus 2 plus 0i. The reason we want to think of them as complex numbers is because we want to plot them in the complex plane. So if we build an axis, a vertical axis, that's going to be the imaginary axis, and a horizontal axis is the real axis. I can plot 2 plus 0i and 2 minus 0i. Sorry, negative 2 plus 0i. Those are our two square roots of 4. They're evenly dividing up the circle. There's 180 degrees in between them. Every number has two square roots. Since we have complex number technology, we could say that negative 4 also has two square roots. (2i) and minus 2i. Two square roots. 2i and minus 2i. If I square 2i, I get 4i squared, and I squared is negative 1. If I square negative 2i, negative 2 squared is positive 4, but then we have I squared, which is negative 1. So there are two numbers such that when you square them, you end up with negative 4. When we write these as complex numbers, there's zero real part. So this 2i is 0 plus 2i, and the minus 2i is 0 minus 2i. If we plot these on these two square roots of -4 on the complex plane, they will be 180 degrees apart. So I go 0 on the real and 2 plus 2 on the imaginary, I'll be at 0 plus 2i. And if I go 0 on the real and minus 2 on the imaginary, we'll be at 0 minus 2i. And they are both 180 degrees apart. I'm going to double up again and go up to fourth roots. So if we think about fourth roots, numbers will have 4 complex fourth roots. That are 90 degrees apart. In the complex plane. Every number will have 4 complex fourth roots. If we allow complex numbers, there are 4 numbers we can raise to the 4th power and come up with any number. So for example, I'm going to go with 16 so I can keep using 2. 16 has 4 4 fourth roots. 90 degrees apart. So I have 2, -2, 2i, and -2i. If I raise each of these 4 numbers to a 4th power, we'll end up with 16. So 2 to the 4th is 16. No problem. With -2, if I take -2 to the 4th power, the negatives cancel out, so I get 16. For 2i, if I raise 2i to the 4th power, 2 to the 4th is 16, and I to the 4th is I to the 4th, but I to the 4th is 1. So we end up with 16. And if I have negative 2i to the fourth power, the same thing happens because negative 2 to the fourth power is 16. I to the fourth power is I to the fourth, which is equal to 1. So there are 4 numbers such that when you raise them to the fourth power, you end up with 16. 16 has 4 fourth roots. If we plot them in the complex plane, they will be 90 degrees apart. So 2 will be up here, 2 plus 0i. Then down here we'll have negative 2, which is negative 2 plus 0i. Then I'll have positive 2i. That will be 0 plus 2i. And we'll have a negative 2i. 0 minus 2i. I know we ventured right into algebra. They're like, oh, dude, this all sounds like algebra. I thought this was trigonometry. How are you getting all this algebra in my trigonometry? It's all connected. You can't just separate everything out. It's all connected. You might be driving an electric car, which is good, but that car came from somewhere, which means it got shipped from somewhere, which is bad. Even if it only got shipped from Fresno, all the parts to make that car did not originate in Fresno. Those parts originated from all over the world, which means they went overseas, which means they're creating an awful mess because the ships make lots of pollution. So everything is connected. Not making fun if you drive an electric car. It's totally a good idea. I should be driving an electric car. I've got a sub 5 mile commute and there are charging stations where I work. I should be driving an electric car. Probably the next car that I buy will be an electric car. But my latest car is not, so I guess I'm a bad person. At least I'm trying to reduce the amount of time that I spent driving. You know what I mean? Maybe that should be the goal. Not drive so much. Maybe the electric cars, by the way, are also a bad solution because it still relies on everybody buying their own car. That's what makes this not work. The fact that if we all bought electric cars, we'd still kind of be boned. You know what I mean? It's all bad. Individual transportation. The amount of time that we spent driving, that's unreasonable. I try to do my part. I didn't drive an electric car, but I had a car. I just sold my last car, was 9 years old, and had 37,000 miles on it. So I try to reduce the amount that I drove. Not really out of trying to take care of the world. More the fact that I just happened to move really close to work. And so I was just driving a lot less. Incidentally, if you want to make yourself happier, drive less. They're like, oh, well, why are you making us drive to school? It's like, I'm trying to not make you drive to school. But some people have decided that we have to drive. You know what I mean? Like, well, yay, let's all go back to school. It's like, well, that means commuting again. And I'm not here for it. Like, it's one thing if you're like an elementary school kid. You can't even drive anyway. And there are more elementary schools. You're probably closer. You just walk there. Anyway, what are we on about? Oh, yeah, complex roots. See, they come out of nowhere. But this 90 degrees apart thing, that's where the trig comes in. It's 90 degrees, so I can use a right angle. So let's get to the point that we want to make. So far, we know that each number has two square roots that are 180 degrees apart, four fourth roots that are 90 degrees apart. Last week, we saw that one had three cube roots that were 120 degrees apart. So let me get right to the point that we wanted to make originally. Every number has nth roots that are 360 degrees divided by n apart. "32 has 5 fifth roots that are 72 degrees apart. One of these fifth roots is real. Since 2 to the fifth is 32, that means 2 is one of the fifth roots of 32. There are 4 more that are complex. We can solve this problem algebraically, or we can solve it with trigonometry like we're going to do today. So if we're going to find the 5 fifth roots, or the 4 complex fifth roots of 32, we already have 1 and 2. We know they're 72 degrees apart. So if I imagine a circle, that's one of the better circles that I've drawn. I'm glad I scanned these notes. Only a little bit squish. Now I just totally missed the middle, so that's oh well. Oh, these aren't x and y. This is real and imaginary. Two plus 0i is the one that is the real one that we have. It's the only one that's going to land on the real axis. That's 2 plus 0i. The other four are going to be 72 degrees apart. So there's going to be one at 72 degrees. Then there's going to be another one 72 degrees later at 144 degrees. So that'll be in the second quadrant. Because they're 72 degrees apart. There'll be a third one 72 degrees later. So 210, 216. And there'll be another, a fourth one 72 degrees later. '72 because the 5/5 roots of 32 are going to divide up that 360 degrees. It'll be 72 degrees apart. And that one will be in the fourth quadrant because 216 plus 72 is negative 72. That was cheap. Would that be 288? Any questions? 5/5 roots, they're going to be 72 degrees apart because 360 divided by 5 is 72. So we want to find these rather than solving algebraically, since we know where they're going to be in the complex plane, we can just use trigonometry to find out where they are. Because if we're at the point on the circle of radius 2, that's 72 degrees up from the positive x-axis. That'll be 2 cosine 72 and 2 sine 72. So the coordinates here will be 2 cosine 72 and 2 sine of 72. So 0.618 and 2 sine of 72 is 1.902. Oops. I just got out of a multivariable calculus class. Sorry, I'm writing vectors. The x-coordinate, what we would call the x-coordinate in the Cartesian plane, is the real coordinate in the complex plane. What we would call the y-coordinate in the a Cartesian plane will be the imaginary coordinate in the complex plane. Notice that we've also got one down below at negative 72. And so that one is going to be at 0.618 minus 1.902 I. So there's the one in quadrant 2. And here's the one in quadrant 4. Here's stuff, go ahead. So I thought about this point 2 units away from the origin, 72 degrees above the positive real axis. And so the coordinates there will be 2 cosine 72 and 2 sine of 72. So that's where those numbers came from. The radius times a cosine, and then the radius times the sine. And then down at the bottom, it would be 2 times the cosine of 288 and 2 times the sine of 288. Questions? For the other 2, for the one in quadrant 2, oh, that was the quadrant 1 one, not quadrant 2, quadrant 1. In quadrant 2, that point will be at 2 cosine of 144 and 2 sine of 144. So this is going to give us our root in quadrant 2. So I need cosine times 2. We get negative 1.618. We expected that. We're in quadrant 2. The x-coordinate is negative. And we're going to get a positive y-coordinate because we're in quadrant 2 and sine is positive in quadrant 2. And then for the 5th root that we have in quadrant 3, that will be at 2 times the cosine of 216 and 2 times the sine of 216. And we get some possibly suspicious looking results. Notice that the other 5th roots of 32 are coming in what we call conjugate pairs. The real part is the same, the imaginary part is opposite. We can see that the 72 is the same reference angle for 72 and 288. But the reference angle for 144 is 180 minus 144. 36 degrees. And the reference angle for 216 is going to be 216 minus 180, which is also 36 degrees. I may have cheated on that last one. You can tell I was cheating because I was using movie typing. I know how movie typing works. It's just too, and they never touch the mouse. What the hell? How do you operate a computer and never like reach over and just like, because at one point there's going to be like tab a bunch of times. Because you're going to have to move to some other field, and rather than grab the mouse and just click there, you're going to go tab, 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 tab. Oh, I passed it. Tab, 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 tab. Yeah. There's far too much fake typing. When I hear that an actor does his own stunts, I'm like, all right, type. And I go, that's gibberish. You don't do your own stunts. My favorite was a show where there's this person, it's like, oh no, we're getting hacked. I'll try to stop it. They're typing. And then the person standing next to them is like, oh no, it's not working. They put their hands on the same keyboard and they were all four hands were just typing. That's not how that works. I mean, like, I'm no hacker, but that's not how typing works. If you got two people that can type like that really fast, they need to take that show on the road. And then it's like, all right, I know you all can type individually, but can you type duet style? And then they like type something out. So like one person starts typing something, then the other person comes in and like starts typing, and they just make a coherent thing appear on the screen. I don't know how popular that show would be, but I'm sure they'd go viral on the YouTube. Here's what we want to notice about these four complex roots of 32. Complex roots of real numbers come in conjugate pairs. Complex roots of real numbers always come in conjugate pairs. Complex roots of real numbers always come in conjugate pairs. The real part A plus or minus the imaginary part BI. The 5/5 roots of 32, the real one was 2. These first two, 0.1618 plus or minus 1.902i, those are conjugate pairs. 1.618 plus negative 1.618 plus or minus 1.716, those are conjugate pairs. The real part is the same, the imaginary part is opposite. This happened in our previous examples. When we looked at the fourth roots of 4, we had 2 plus 0i. That's one of the real roots. The other real root is negative 2 plus 0i. But the other pair, the pair of complex zeros, is 0 plus and minus 2i, conjugate pairs. Any questions? How's everybody okay? What we did was use trigonometry to solve this algebra problem. we could think of this problem where 32 has 5/5 roots. The 5/5 roots of 32 are all solutions to x to the 5th equals 32. Now I'm back to algebra. So the 5/5 roots of 32 are the complex solutions to this equation. X to the 5th is 32. This is just an equation form of asking the question, what are the 5th roots of 32? We know there's one real one, that's the 2. This is further connected to algebra, because the roots of the solutions to this equation, the complex solutions to this equation, we can see also factors of x to the 5th minus 32. Or the solutions to x to the 5th minus 32 equals 0. That's just what I use for the example. Moreover, this is all still tied to the stuff that we know about factoring polynomials. Since 2 is a solution, or a solution to the polynomial equation x to the 5th minus 32 equals 0. Or we could say 2 is a 0 of x to the 5th minus 32. Equations have solutions. Polynomials have zeros. But since 2 is a 0 of x to the 5th minus 32, that means x minus 2 is a factor of x to the 5th minus 32. That is x to the 5th minus 32. One of the factors is x minus 2, and then there's some 4th degree polynomial. But wait, there's more. This is some 4th degree polynomial that has to have 4 complex zeros. Those complex zeros have to come in conjugate pair. A plus or minus BI. Conjugate pairs come from quadratics. So we can write this fourth degree polynomial as 2 quadratics. One of those quadratics gives us conjugate pairs, 0.618 plus and minus 1.902. And the other quadratic gives us the other pair. So we can really see how the structure in algebra and the structure in trigonometry come together with these polar coordinates and these complex numbers. Is everybody okay? No is correct. I'm making reference to a bunch of algebra that for the most part, we don't talk about in algebra class. A lot of times we take algebra and we say, okay, now you're done with algebra, but you're never done with algebra. Algebra never goes away. Eventually, y'all going to be in Calc 2. I'm going to say, all right, wait for our next integration, which is partial fraction decomposition. And then it'll be done in the context of calculus, but it's just algebra. And like partway through that, you're going to go, hang on a second. You're going to be doing the homework. So hang on a second. Is this partial fraction decomposition shit just algebra? And they go, ha ha, you found me out. But it's too late. We're well past the last day to withdraw from the class, so you're stuck now. See, that's how it works. It's all just an evil scheme. How's everybody okay? It gets even better, by the way, because since we're not okay with this, with all this stuff, it's too much. Let's do more. Since it's too much right now, let's do more. If x minus 2 is one of the factors of x to the 5th minus 32, that means if I take x to the 5th minus 32 and divide it by x minus 2, we'll figure out what that 4th degree polynomial is. Because that's just how multiplication and division get along, right? If x to the 5th minus 32 is x minus 2 times some 4th degree polynomial, that means x to the 5th minus 32 over x minus 2 divided by x minus 2 will be some 4th degree polynomial. If 2 times 3 is equal to 6, then 6 divided by 3 is equal to 2. So if we want to figure out what that 4th degree polynomial is, we got one of the real zeros of x to the 5th minus 32. We can just divide. And everybody remembers how to divide, right? When it's polynomials. Everybody remember long division? Not when it's like this. This long division is, if you're familiar with the long division game, this long division is the same long division that you're familiar with. So just as if I wanted to take 7 into 238. We say, how many times can we subtract 7 from 2 without going negative? Yeah, we can't do that. Not without going negative. How many times can we subtract 7 from 23 without going negative? That's 3 times. But we're not actually subtracting from 23. We do 3 times 7 is 21, but this 3 is in the 10 spot, so it's actually 30. We're subtracting 37s from 238, and that's 210. And then so we subtract. That leaves 18. How many 7s? Wait, 28. This is why I normally don't sidebar arithmetic, unless I prepared it ahead of time. How many times can I subtract 7 from 28? That's 4. So let's subtract 4 7s. We're going to do the same thing with these polynomials. You're not going to like it. I can tell you're not going to like it. I'm not going to like this thing. It looks like this. I can see it through the mask because it looks like this. That's the "are you shitting me" feature. Thanks. How many times can I subtract x minus 2 from x to the 5th without going negative? Well, to even do that subtraction, I have to multiply x times x to the 4th. X to the 4th times x squared is x to the 5th. X to the 4th minus 2 times minus 2 is minus 2 x to the 4th. That's the same thing we did over here. We said 30 times 7 is 210. Subtract the 210 from the 238. Here's the tricky part. We're subtracting its polynomials. No one likes that. The words that I was taught was you bring down, but you don't have to bring down. You don't have to leave a space or bring down or do any of that bullshit. Because you're not subtracting 7 from 238 3 times. You're doing that 30 times. That's why the 3 is in the 10s spot. So we're not bringing down the 8. It's just that 8 minus 0 is 8. We're not bringing down the 8. 8 minus 0 is 8. It looks like we're bringing it down, but every time your teacher said bring down the 8, they were moving you further away of understanding what the fuck was going on in your long division problem. And then when you got to polynomial long division, one of the reasons that you hated it so much was that you were never really understanding what you were doing with the numbers. You were proficient at it, but you didn't understand what was going on. Does that make sense? This happens a lot. It's perfectly normal. A lot of you drove here today in a car with an internal combustion engine, and you cannot explain to me how your internal combustion engine works, yet still, here you are. How does a torque converter work? I don't know, but here you are. It makes the car easier to drive. That's all that matters. So now I need to subtract the x from a 2x to the 4th, just like I did over here. All I'm doing is subtracting a bunch of x minus 2s from x to the 5th minus 32. So I need to multiply by a 2 and an x to the 3rd, just so I can subtract them, because we can only subtract things that are the same. And then we just keep going. Oh, just like we thought, some fourth degree polynomial. Is everybody okay? Probably not, but that's okay. We're making bigger connections. And we're utilizing something that's kind of important that almost never gets discussed in algebra classes. You'd think if you've been through a bunch of algebra classes that you'd recognize the fundamental theorem of algebra. Sounds like it should be an important aspect of algebra. But we usually don't talk about the fundamental theorem of algebra in algebra class. It's too soon to bring up the important stuff. Any questions? I want to reiterate that this kind of stuff where we're connecting our complex roots of real numbers to complex zeros of polynomials to factoring and all these algebra things. These are not things that you need to be proficient in your future career as a whatever you're going to be. It's not like you're going to be sitting at your desk in your cubicle and your boss is going to come up to you and say, I'm going to need you to factor this polynomial before you leave today. That would be great. That's not going to happen. And if you're working in some technical job and you're about to factor a polynomial by hand using the rational zero theorem and Descartes' rule of signs, if you ain't a math teacher, you're about to get fired. Boss like, oh, so what you up to there? Well, I'm about to factor this polynomial. You'd be like, oh, by hand? And then you'd be like, oh, yeah. You'd be like, oh, just like Luke taught me. He's like, oh, nah, forget that guy. Get out. Gather your stuff. Security, get down here. That's not the point. You know what I mean? We're going for understanding, not proficiency. It would be nice if everybody in the room could have the same goal, but we necessarily don't. I want you to learn how math works. You just want to get out of here so you can get it in the next class. I mean, think about it. Don't tell me because you know what the answer is supposed to be. I know that you know what the answer is supposed to be. But if you had these big piles of money, would you do this fine? You like to think that you'd be like, oh, no, I care about my education. You'll care about your education right up to the point where you have big piles of money and you don't have to do anything. Because if you got enough money, if you need a degree, you just go buy one. You know what I mean? I don't know how many of you have a life goal of being extraordinarily wealthy. But if your goal is to be extraordinarily wealthy and your parents aren't already extraordinarily wealthy, you've already fucked up. You've already made it way more difficult. If you want to be super wealthy, the best thing to do is be born super wealthy. What are y'all doing here? Go back and, oh, that's right. Wasn't really up to you. You know what I mean? All right. So I don't want you to get stressed out that you're going to have to do long division of polynomials. And I didn't even finish this problem because this fourth degree polynomial factors down into two quadratics. But we didn't talk about that kind of factoring. What are we doing as pi terms? We don't have to anymore. Because we could just be like, oh, hey, Siri, what are the complex zeros of x to the fifth minus 32?
Okay, I found this on the web for what are the complex zeros of x to the fifth 32. Check it out.
Oh. It's not about remembering this stuff. It's like the fact that I remember this stuff, that makes me weird. That's unusual. That's strange. What the fuck is wrong with you that you remember this? I don't know. It's cool. I bet there's a lot of stuff that you remember that is pretty useless as well. I don't know if you're familiar with miniature war game, but there's one called 40K, and it originally came out in the 90s. It was called Rogue Trader. And I remember that a melt-a-gun had a range of 12 inches, 8 strength, and did a D6 damage. Why do I fucking remember this? Why do I remember this and forget that I have a meeting on the first Friday of every month? How does this work? What I want to explain to you is that we like to pretend that we're rational, that we think about things. Most of our rational thinking is rationalization to justify all the irrational decisions that we make. You know what I mean? You think you're being rational, but really you're just being an idiot and trying to justify that. You're being irrational. You're making bad decisions and justifying that with some kind of reasons. The rational thing for me to have is an electric car. I can just charge to work and take that 5 miles. I did not replace my last car with an electric car. It's irrational. There is no reason for me to drive the car that I'm driving. No rational reason. Plenty of reasons, but none of them are actually reasonable. All right, that's going to do it for today. I will see you all on, I think Thursday is a flex day, is it not? Everybody, all students always know when there's no class. I don't have to know. If the students are like, oh, no. If I'm like, I'll see you on Thursday, they're like, oh, no, you will not. All right, that's it for this week. I'll see y'all on Tuesday. Everybody have a good flex day and a good weekend. Thanks for playing.